Okay. Yeah, so good morning, everyone. So this is our second class, and I don't know how excited you are, but you should be a little excited because this thing everybody's been talking about, neural networks, today we're going to demystify it. So we're finally going to learn what neural networks are, and the way it's going to be, we're going to go to the point we left off the last time we met and talk about feature transform, and this will bring us to the idea of a neural network, and we'll define what it is and what it's made of. Then we're going to make this quick reminder about derivatives and chain rule, because this will help us better spend most of our time on understanding the algorithm for training neural networks, which is the backpropagation. Then we're going to generalize things up. So we're going to expand our understanding of networks to something that is not that strict to the types of layers that we saw before. And we'll end with some demo showing a little bit of how these things work. And I just want to say one important comment. So we're going to dig in, especially to this backpropagation. We're going to dig in and to figure out all the nuts and bolts there. And this is important to graduate students and those who want to conduct research in neural networks. You will see many people working with neural networks, not really following how backpropagation works and everything, and it's fine. People can work this way, like a black box, and we use it, we optimize, and whatever. But the difference, I mean, understanding the true algorithm and those things, don't let people tell you, oh, backpropagation, it's just some chain rule, and then later those people, when they actually have to deal with stuff, they don't really follow. So these minor details, they make a difference. This is what I'm trying to say. And let's go back to where we left off. So if you remember what we discussed last time, right before, I mean, we had some overfitting and underfitting discussion, but right before that, we talked about this thing called feature transform. And the idea was that if we have some input, we can apply some transformation, and this transformation can take us to have more dimensions than the original input actually had. Then we can apply linear hypothesis that we dealt with a lot the last time, if you remember linear regression. And I believe that in the tutorial you were working on linear classification. So this whole thing actually is encapsulated in this nonlinear hypothesis. So this is kind of and if you remember last time we used it, we did this polynomial regression, if you remember. So you can do many things you can use for this transformation so that you can actually fit nonlinear hypotheses. But here is where neural networks get better than just doing this thing. So the idea of neural networks is that this part is learnable. So we are entering a world that people sometimes refer to as representation learning. So the idea here is that not only we do some transformation to our data that we can later use and to fit according to our objective, the representation itself is learned. And not only that, so last time we were kind of talking about, okay, we do this transformation, we have this representation, and then we have some hypothesis, some linear maybe hypothesis on top of it. But it's actually even more than this, because it's going to be this hierarchy. So it's going to be at every what we call layer, we're going to have a representation of the data until we finally get to the output. Okay? So this is hierarchical representation learning, and this is the main idea behind the existence of neural networks, why people really wanted to do them. So there was some neuroscience inspiration for it, and some may claim about similar things in animals' brains. But this is the main idea. This is what we're going to go after today. This is the goal. And the way we're going to achieve this is using this thing called artificial neural network. And as I mentioned, this is vaguely inspired by the biological neural networks. And I don't know if there are neuroscientists here, but if there are, they probably know about this more than I do. So I'm not going to do sometimes people do intro about neuroscience, which I kind of find it's only vaguely related, and also many of the mechanisms in artificial neural networks work very different than what biological neural networks work with. So if anybody interested in this topic, you can read about it or learn about neural networks, biological neural networks. So we're going to familiarize ourselves with this mechanism, with this set of mechanisms. So here's how it's built. We're going to have this input vector, and we're going to have an output vector. And in between, what we have is this bunch of layers that we refer to as hidden layers. And these are called hidden because they're not in the input and not in the output. And when just applying the network, we don't actually get to see them. Of course, it's easy to see them if you really want to. And here's how technically we're going to refer to these. So every circle that you see here, we can refer to it as a neuron. And we're going to enumerate them so that the superscript is the layer number. So the input is layer 0, okay? And the subscript is the number of the neuron inside this layer, okay? And so we can enumerate all the other neurons that we have, and the last one, the output vector, we're going to use capital L as this last layer. Now, this is not something that everyone does the same. These are notations that we use for us so that we can easily derive everything that we need. Okay. And in between those layers of neurons, we're going to have these arrows that we call the weights or parameters. So these are going to be the things that are going to later train and change when we do the training phase. And these are built such that between every two layers, every neuron is connected to any other neuron. I should say this is the most basic neural network, sometimes referred to it as a vanilla neural network, and the layers that make up a vanilla neural network, or sometimes they call it multi-layer perceptron, so MLP, and the layers that make this type of network, they are layers that we sometimes call fully connected layers. And they're called this way because they're fully connected. Every neuron is connected to every neuron at the layer before, and we're going to have notation for these weights too. So I refer to them with W, and again, the superscript is the number of the layer, and I'm going to use the layer that is going to come ahead, not the layer before, but the layer is after. And then there are two subscripts, and this is simply going from number 3 to number 1. Okay, so it symbolizes from which neuron in the previous layer to which neuron in the current layer. Are we good? Is this clear? Great. All right. So having this in mind, we're going to define a function for each of these neurons. So each of these neurons, when we apply the network, when we click play, is going to get a value. And this value is going to be the result of a function for each one of them. And the function that we're going to have for some neuron, for the neuron layer L and the number J neuron, is going to define this way. So for example, we're looking at this X11 neuron, and we're looking at all the weights from the previous layer that are connected to this neuron. And the first action that we're going to do is the linear action that you are, I think you're already familiarized with. So this is just summation in which we multiply every weight with the neuron that it came from, and we sum it all up. Sound good? This is the first thing we do. The next thing we do is we're going to add this thing, we call it the bias, okay? And this is very similar to linear regression so far, right? You have all the weights multiplying those x's, and then you have another sort of weight, another parameter that you're not seeing in the picture now, except for I added it here, okay? That is simply adding some value to the results, okay? Just like you do in linear regression. And then finally, after you do all that, we're going to apply this function that we annotate as sigma. And this is going to be a non-linear function. We sometimes call this an activation function. And it can be many things, but there are some that are very common, what we usually use. So I think you know some of these already from the tutorial. So the common possibilities are the sigmoid. You did learn about sigmoid in the tutorial, right? So you know what a sigmoid is. So this is one option. There is a hyperbolic tangent, and in case you never noticed this effect, so it's exactly the same as sigmoid. That it's just that you stretch it to be between -1 and 1, except from between 0 to 1. You can see that. Okay, and then the last one is called ReLU. ReLU stands for rectified linear unit. It's a very, very simple function. It's simply a function that says if you're negative, you're going to be 0. That's it. If you're positive, I do nothing. If you see nothing happens, the identity, but it kills negative values. Okay, so everything coming out, if you use the ReLUs, the value after the activation is always going to be non-negative. So far, so good? All right. So this is what every neuron does, okay? Now, it's going to be more productive for us to look at not at single neurons, but at layers of neurons as if they are vectors. And then we're going to take this bunch of weights that we have at each layer. And what do you think these should be? These are matrices, exactly. And you can see why. So for example, what is going to be the size of this matrix W super 1? Any idea? 4 by 4, yes, exactly. Going to be a 4 by 4 matrix because it connects 4 input neurons to 4 output neurons for that layer. So now we can formalize our rule as a vector rule rather than scalar rule. So if we think about a vector of neurons, the function for it is going to be multiplying the matrix, the W matrix, transposed with the previous layer. You can think about this transpose later. It's just this, it's very arbitrary. It's because of the way we define the subscripts. We said going from 1 to 3, so it's going to be 1, 3, right? So if you think about it, one way to think about it is if you have different input and different output sizes, then think about what the shape of the matrix should be. This is why we need this transpose. So we multiply it by the previous vector, then we add the bias vector, which is just the list of the biases for all the neurons in this vector. Okay? And then we apply this nonlinear activation function, which now which is now a vectoric function, but mostly, almost always, it's just going to be a pointwise function. So it's the same as, so when I say sigma of this vector, it simply means that I apply this function to every neuron separately. Okay, are we good? So this is the rule of a neural layer. All right. Now, when we apply this, we do this thing we call feed forward. It means I come with some input, I apply the network to it to get my output, and the way I do it is that every layer is going to be calculated sequentially. So I get the input, I apply all the weights, get the next out, the next layer, until I get to the end of it. And this is called the feed forward of the neural network. Are we good? Great. Or the forward propagation. Now I have a question for you. Why is it so important to have this activation function, and specifically a non-linear function applied here? Why do I insist on making life harder? What would have happened if I didn't have it?
It was only one layer.
Multiplications will condense into one.
Exactly. So if all the layers are linear, and you can see them as like multiplying by a matrix again. So you can take all these matrices, multiply them together, and eventually what you get here is just what? Linear regression. Just like multiplying by a single matrix. Yes.
It's not really linear, right?
Why not? Because of the bias?
Yes.
So the trick with the bias is that you're right, it's not linear, it's the correct term is affine. And a nice way to look at it is if you say, so for every layer, I'm going to add 1 as one of the neuron, like the value 1, and then the bias is like another weight, and then it's linear for that. But you're right, it's a good observation that it's not truly mathematically linear with respect to the input. It's affine. Okay. Great. So going back to our motivation, remember what we started with. We said we wanted this learned feature transform, and this is exactly what we're getting. Okay, so we have all these. You can view this as you're doing all these layers, doing feature transformation to get you to this representation. It's nice to think about the next to the last layer, and this representation is then undergoes this last thing, which in many cases doesn't have to be, but in many cases it's going to be linear. And this is what we finally get as our initial motivation. You do the feature transformation, you apply something to it, but you can also think about every layer as some representation of the data in the context that we care about. Okay, so you just keep re-representing your input at every layer until you get what you want. Quick question: what do you call a single layered network? Linear regression if it's regression, and it can also be logistic regression if you had this, for example, a sigmoid at the end. So there is a fancy way of calling logistic regression a single layer feed forward neural network with sigmoid activation. Okay. This was the easy part. This was the forward propagation part. Okay. And now what we're going to spend most of our time doing is understanding how we train this thing, because we know how you apply it, we know the rules, everything stays. Now we need to train this. If you train this, it means that you don't only have inputs. What else do you have? In order to train some algorithms. Sorry? Labels. Exactly. Okay. So I'm going to train this network. So I have this long list of inputs and labels in my training set, and I'm going to have to train this using those pairs of inputs and outputs. This is supervised learning. Okay. and I'm going to have some loss, right? And let me just remind you that previously we talked about that when you have a supervised learning algorithm, you need three things. You need the hypothesis, right? You need the loss, and you need the optimization algorithm, right? So the hypothesis class is you can think about it is for a specific architecture of a network. When I say architecture, I mean like the number of layers, the number of neurons, each layer, etc. So the hypothesis class just contains every possible set of values for all the parameters in the network. Okay, are you with me? The loss can be many things. We can define it. And the optimization algorithm is going to be based on an algorithm that we learned the last time that is called gradient descent. So we're going to do gradient descent to minimize this loss for finding, or we're going to do gradient descent to find the hypothesis that minimizes the loss that we define. So the goal is clear. The hard part, not very hard, it's all just technical, but the part we're going to spend time on, what do you need for gradient descent?
Gradients.
The gradients. That was an easy one. For gradient descent, you need the gradient. Okay? So the thing we're going to spend time on is finding the gradient. And we're going to first see that it's not trivial, because think about it. What we actually need is the derivative of our loss. The loss, you can think about the loss, for example, as MC, okay, between what I predict and this, or other losses, for example, for classification that you learned in the tutorial. So the same losses for linear classification can be used here. And I actually need the derivative of this loss with respect to every weight, every arrow I see in the network and the biases. By the way, when you see this theta, it's just a short way for me to write W and B together. So all the parameters, both weights and biases. Okay. So coming to the challenge of trying to take the gradient, I'm looking at the function of example for of one of the neurons in the last layer, like an output neuron, and I'm trying to figure out if I can get the derivative here. So if I want for example, the derivative with respect to some weight, I don't know, this weight in one of the first layers, I'm not seeing it. So look at this function. What I see here. So I see this. I see W superscript L. So these are weights from the last layer, and I see bias from the last layer, and I see inputs. I mean neurons from the almost last layer. So where is the? Why don't I see, for example, this weight in this expression? Where is it hiding? In X, that's correct. So remember that we apply the layers sequentially. So this X from layer L minus 1 can be now extracted as its own function. Okay, and then I can see X as L minus 2, which is still not getting me here. So if I want to get all the way to the bottom, right, it's going to be very heavy, right? Because it's going to go on, and every time that I have this summation on all the possible routes going through all the possible neurons. So trying to take the derivative of this thing is going to be an incredibly large sum of elements, which if you think about it, is all the possible routes going from the neuron it gets to the end. This can be, think about if you have 200 layers and I don't know, and thousands of neurons in each layer. This is sort of intractable, and also it's dynamic. So we do this in one step. The next time we do it, it's not going to be the same function because it's going to all those values, all the other W's, those that I don't take the derivative with respect to them, they're also changing at every step because I update them. And if you do stochastic gradient descent, the input changes, so all the excess input, and you can see it's not feasible, right? You're all with me? We're understanding each other? Are we good? Okay. So this is the problem we're having, and we're going to try to solve it. But first, we're going to remind ourselves some very basic facts about gradients and derivatives. And here is the first one, which I believe most of you are aware of. And this is the basic chain rule for derivatives. So say I have a function f and a function g, and then I look at the function f of g of x, and I want to take its derivative. So it's going to be, yeah.
That the function is dynamic. I mean, the values of the weights change every time, but the form of the function is always the same.
Right, but it's not the same. So for the next step, it's not going to be the same derivative, not only because the thing you take the derivative with respect to change, but also other things, right? Because the function looks like W1, W2, W3, X1, X1, you only care about Xi. So usually you have a function like a derivative function, and you can just plug in whatever X you want and you get the derivative with respect to it.
Yes.
But here the entire function changed because at the next step, you take derivative with respect to some Xi or to some Wi, but all the other W's changed, all the other X's changed. So it's a whole other function. It has roughly the same structure of this, summation thing. Okay. But it's not just a function that you calculate once and then you put everything again. You need to recalculate everything every time. All right. So I believe most of you are aware of this. So the way you solve it is you say, okay, I'm going to take the derivative of f, and I'm going to plug in the value. It's like a frozen value of g of x. So I'm taking the derivative at this point. And then what I have to do is to multiply it by this internal derivative, by the derivative of g with respect to x. We're good about this one, right? We're good? Okay, but this is what it looks like graphically. So say I have y equals f of x and z equals g of y. I can look at this graph and say, okay, fine, g applied to x, giving me y, then f is applied and I get z. And then at the Leibniz way of writing things, when I take the derivative of z with respect to x, it's going to be this thing. I always think about it whenever you have a derivative, I do this. You can always do this thing, right? You take the bottom, you take the top part, and then you do this, right?
Is it the opposite? It's like Z f of y.
Z what? Sorry?
Isn't Z application of f on y?
Yeah, sorry. Yeah, G and F got mixed. Thanks. Yeah, Z is f of y, y is g of x. Yes, sorry for this. Yeah. So anyway, you get this some derivative like in the Leibniz form. It seems you can always do this thing. You take the bottom part, you take the top part, you do this, separate them. Now you can put whatever you want that is the same in both sides, as long as it's differentiable by x and z is differentiable by it. So what I mean, it looks like this. I do this thing, and now I can put whatever I want as long as it's nice enough. And in this case, I put y. And this is what the chain will look like. I realize that you know basic calculus, and this isn't new for you, but I'm showing this for us to get into the spirit of understanding the chain rule. So if I want dz of dx, I first go dz over dy, and then I multiply it by dy over dx. We're good, right? Okay. Now what happens when we have more than one route? So for example, if I have a multivariate function, z, and it has two inputs, it has y1 and y2. And each of them, y1 and y2, are functions of x. So this is what the graph looks like. And now I ask myself, what is the derivative with respect to x? And the thing here is that what's different from before is that we have another route. So I take this of the x. So it's dz over dy1 multiplied by dy1 over dx. And then I do the same for the bottom part. It's dz over dy2 multiplied by dy2 over dx. Okay? And here's the important part. I have these two routes of arrows getting to x, and the way I combine them is by simple arithmetic summation. Okay? And this can be easily shown algebraically with the definition of derivatives, if you will, or intuitively think about it. I have this mountain that I'm climbing, and I know that, and I'm taking very small steps, and I know that if I take a step to this direction, I'm going to gain some elevation. And if I take a step to this direction, I'm going to also get some elevation. And then if I combine them both, I do this and then that, assuming everything is small and linear where I stand, then what I get is just the sum of gains from all the directions that I took. So let's do a very help me here with a very quick tutorial-ish way of checking that we know how things go. So let's say these are our functions. So we have y1 and y2, and we have z as a function of both y1 and y2. And let's actually solve this. So let's start. What is dz over dy1? Can anyone tell me? Sorry? 3. Yes, it's 3. And then what is dy1 over dx?
X plus 2z to the 2x.
Exactly right. Okay, and now we just need dz over dy2. It's 2y2, which is actually 2e to 2x, right? 2e to the x, and then it's e to the x, and then we get the final derivative, which is summing both of these, and we get this 12x plus 8e to the x to the 2x. And just to make sure that we're not crazy, in this specific case, we can reformulate z as a function of x. We just plug in what y1 and y2 is, and you can check that if I then take the derivative of this. So you see, I get exactly what I need. It's 12x plus 8e to the 2x. And sorry if this was too basic for some of you, but here's the important conclusion of what we just did here. And the conclusion is, whenever you see this pattern, so x goes to many nodes, and then the many nodes goes to z, whatever, doesn't have to be x and z, of course. Okay, so the derivative of z with respect to x is going to be a summation. A summation of what? A summation of all the multiplications of derivatives across all possible routes going here. So it's going to go through every possible y. Let's make sure I put the same y here and here. Okay, and I sum all of them. So when I change x by a little, it changes all those y's, and each of them has a contribution to the elevation that z gains because of the change of x. So I sum them all up. And I'm showing this because in a few slides, I want you to be able to recognize somewhere this pattern and then to help me solve what we need to solve there. Okay. So here is how we're going to approach our challenge of getting the gradient of all the weights and biases in a neural net. So this is the function that we have for every neuron, and I'm going to annotate this this thing in the brackets. I'm going to annotate it as z, just so it can help us later to write things shortly when we need it. And looking at the derivative with respect of the loss with respect to some weight in the network, I'm going to use the chain rule that we've just seen, and I'm going to split it into this multiplication, to factorize it, maybe the better term. And what I'm going to do is I'm going to say, fine, I need the derivative with respect to this weight in layer L. So I'm going to split it in two. I'm going to take the multiplication of the derivative with respect to the neuron that this weight points to. So picture the arrow points to a neuron. I'm going to take the derivative with respect to this neuron and then multiply it by the derivative of the value of this neuron with respect to this weight. Legal, right? Legit? Okay, now here is a question for you. What is this? Can anybody solve this for me? What is the derivative of a neuron with respect to a weight that points to it?
Just the weight.
Sorry?
Just the weight. It's
The weight? Why the weight? It's with respect to the weight.
Yes.
Okay, and you have this here. Okay.
X and the sigma, just the sigma of the derivative and multiplied by x.
Exactly right. The derivative of the nonlinear activation function sigma. Okay, because this is the function we have here. The function we have is sigma. So we need the derivative of sigma, and then we multiply it by the inner derivative. But we only care about one weight. So all this sum, it goes away, and we're only left with this neuron that's on the other side of this arrow of this weight. Okay, we only get this matching neuron from which we came. Okay, because this is what W was multiplied by inside. And of course, we have this thing. The derivative of sigma, this is why I needed the Z thing, okay, at this point Z, where it was activated. And here's the good news. The derivative of sigma is a very easy thing. It looks kind of scary now, I don't know, many Greek letters, whatever. But the derivative of sigma is a very easy thing, usually. So if we look at the common activation functions, so their derivatives are very straightforward. So for sigmoid, so the derivative, you can verify later if you want to, like prove those things, but the derivative of sigmoid function is actually the result might just multiply by 1 minus the result. Okay? And for hyperbolic tangent, maybe some of you know this, so it's like regular tangent. So it's 1 minus hyperbolic tangent squared. And you can see that for ReLU, it's this step function. So it's going to be 1 over here when it's bigger than 0, and then and 0 everywhere else, like in the negative side. So it's going to be like a step function. Okay, are we good? So if you're using ReLUs are the most common today. So think about it that if you are using ReLUs, this scary thing is just either multiplying by 1 or multiplying by 0. Okay, nothing more. Okay, are we good by now? Okay. But here is the part where we need to work harder. Okay, now we need the derivative of the neurons And this is the thing we're going to get by doing this backpropagation. So we're going to define this thing. We're going to call this G. Okay. And our goal is going to be finding all the G's in the network. Once we find all the G's in the network, we do this trick and we get the derivative with respect to all the weights. And this is how we get the gradient. We good? Okay. Let's do a quick break. I'm sorry, but we kind of started late because of the camera thing. So let's take a quick 5 minutes break and then gather here again at exactly 10:05. Okay. So we're after this G, what we call now G. It's the, and just to use words, G. Can you maybe can you close the door? All those things. So G is the gradient of the loss, but with respect not to the weights, but with respect to the actual neuron values. Okay, so it's this list of derivatives of the loss with respect to all the neurons, and once we get that, we can multiply it by this trick, and then we get the true gradient with respect to all the weights. Okay, how do we do this? So let's look at our network, and now for every neuron, we now define two things. We don't only have X now. Okay, we also have G. X is the feed-forward value. Okay, and G is going to be the gradient. So it's going to be the derivative of the loss with respect to that neuron. When we have all the G's, as mentioned, I can use that trick, multiply by the activation derivative and by the neuron that is behind every weight, and then I get the derivative of the loss with respect to each weight. Okay, good. So how do I get these G's? So let's look at the definition again. It's the derivative of the loss with respect to some X, L, J. Now, if we think about some L, we're not sure how we're going to do this. So we have this loss here, and we have this neuron here. So we don't know how to approach this, but maybe we can use the chain rule again to make things a bit easier for us. And the way we're going to do this is we're going to look one layer ahead of the neuron that we care about at this point. Okay, and we know now we can look at all of these neurons. And my question to you, what can I do now? How can I express this now? How can I expand the expression that you see there above? Any idea? Do you recognize this pattern in red here? Anybody recognize this? We've seen this before. So if I want the derivative of the loss with respect to this neuron here, what is it?
It's the sum of the derivatives with respect to previous.
It's the sum of the derivatives that we've seen before, right? It's the sum of these multiplications. The derivative, this derivative multiplied by this multiplied by this, blah, 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 plus, 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 this multiplied by this, sum of all of these. Okay, let's write it down. It doesn't solve yet our problem, but it's another way of looking at it. Okay, so you remember the thing I like to do with my hand? I took the DL and the DX and I did this, and I stuffed it with all the possible X's, all those nodes, and sum it all up. Are we good at this point? Okay. Now, help me out here. Can anybody calculate this highlighted expression? let's say what it is in words. It's the derivative of some neuron with respect to another neuron from the layer before. So, for example, it's kind of the derivative of can be the derivative of this neuron with respect to that neuron. Okay, can anybody help me calculate this? The weight, almost. Exactly. Yes. So you can look at here. What I just asked you is to take the derivative of this expression. Okay. This is so we take the derivative where the derivative of the activation function, then the inner derivative, which has many things that are not influencing us, but only the weight that multiplies this specific neuron that we take the derivative with respect to. Okay, we good? So we have this one solved. Great. What can you tell me about the left expression? What is the L with respect to the neuron in the layer L plus 1? Anybody?
It's the same. It's the same as we did previously. Just for the one layer.
So it's the same meaning, name it.
It's a sum over K.
It's G. Exactly. But it's not G superscript L, but this time it's G superscript L plus 1. Look at the definition of G, and then look at this. Almost the same thing. The only thing that is different is the indices. Okay? Everybody is with me? We okay on this? So what did we get ourselves into here? This is just a sum of G's, but we started with a G. So we got this recursive expression. This expression says that the way to find what G of some neuron is by using all the G's, all the gradients from the neurons one layer forward. You see? How do I get all these G's? So I need all these G's, and then all I have to do is multiply them by these weights and multiply by this derivative thing, and then I get those. Okay, so this is a recursive rule. What does any recursion always need? Initial conditions, or maybe a stopping criterion, right? Where do I stop? And the answer is that if I keep doing this thing, I keep doing it more and more and more, eventually I'll find myself with G capital L. Okay, right? So I get all the way here. Now I'm just going to use this analytic derivative that I have that depends on what the loss function is. So if it's MSE, it's going to be twice the difference. Okay, we good? So I have a stopping criteria. So basically, think about it. If I have this rule, if I have this recursive rule, it means that I can sequentially calculate all the gradients. I'm going to start here. This is why it's called backpropagation, because I know how to calculate G capital L. I need nothing for this. This is like only the last layer, the derivative of the loss with respect to this. Fine. Okay. Then I'm going to ask myself for each neuron here, what is the derivative of the loss with respect to it? And I can use what I already have. So I'm going to do this layer by layer by layer. And remember that we always like to do these things. In a vector way rather than just scalars. So you can think about every layer. I have two vectors. I have the x vector, which is the values from the forward propagation, and now I'm adding the gradients. So it's the values of the back propagation. Okay, and if we take the formulation that we got to in a vectoric way, okay. So again, what do we see here? We see G superscript L So it's this vector G equals the multiplication of the weight matrix, but now it's the weight matrix that is ahead. It's this weight matrix multiplied by this gradient vector, which also needs to be multiplied by this derivative of the activation. But I remind you, don't be alarmed by this thing. So say this is a ReLU network, all activations are ReLU. This is simply means either 0 or 1. So it basically means that some of these I kill them. They just zero. I close the flow. So I'm saying, okay, for this particular step, I'm killing the flow from here to here to there, and all the other I keep. Okay, depending on whether or not this was on or off, meaning the z value was negative or positive prior to applying the ReLU. Yeah.
Sorry, what is the notation of the circle?
Notation of the circle. What? Oh, sorry. It's a point-wise multiplication. So I just multiply every value with this same it's not the same, depends with the derivative of the activation. And another question?
The subscript for the sigma is because we might have different activations for different layers, or
Yeah, I mean it's not different activation, it's different result of the activation, right?
no, the derivative.
The activation function can be the same, but you're going to have a
And
different.
it can be different also.
It can be,
Okay.
but don't go there now. I mean,
No, I'm just wondering why we have a subscript, the sigma prime.
yeah, it's not because it's a different function. This value can be different, right? Because there is a different value before applying it, so it's different value after. So not all the neurons have the same value. And let me ask you this: does this structure remind you of anything you've seen lately? Is it similar to anything like multiplying each time by a matrix? Yeah, it's very similar to the forward propagation, right? In the forward propagation, when an input multiply by matrix, activation, multiply by matrix, activation, multiply by matrix, activation. What do we have here? So it's not exactly the same, but it's very similar if we check it. So you see, in the regular network, we had this activation function of multiplying by W, adding the bias. And what do we have now? It looks almost the same, just a few minor things that are different. So one thing is it's going to be linear activation. So we don't apply any activation function now when we go backward. We don't do the transpose, which only makes sense because we use the weights that are after the layer, not before the layer. So if you think about the sizes, you don't do this transpose now. You do this annoying thing, you multiply by the derivative of the activation function, which you don't do in the regular feed forward, and there is no bias. These are the differences. But now, considering the differences, do you realize how elegant is what you're seeing now? Because basically what I'm telling you now is that when you want to train a neural network, you get your inputs, you get your outputs. Basically what you do is you feed forward, get all the X's, then you do the same type of flow, this neural network type of flow, go backward, multiply by all these matrices, and now you get all the G's. So you get the X's, you get the G's, you get the X's, you get the G's. Okay, and all flows very elegantly in the way of just sequentially, each layer multiplying by these matrices. Okay? Are we okay until this point? I realized the last thing was kind of maybe annoying to follow, so you can look at it again later. It's really just, we didn't bump into any abstract mathematical objective here. All we had is chain rule and derivatives, but these are like those minor details. So you can look at it again later if you couldn't grasp every step. But there is nothing here except for chain rule. Okay, let's go through the entire algorithm of backpropagation. How does it go? So remember the goal. Backpropagation is merely just a way of applying gradient descent to a neural network. Okay, we do gradient descent. This is the algorithm we do. Backpropagation is the way to calculate the gradient. Okay, here is how the algorithm works. We initialize the weight. We start by random values to all the weights in the network and biases. Now we're going to repeat until convergence the following steps. So we sample a batch from the data. So it's a batch of pairs X and Y's. So you see we got our X's, we got our Y's. Then we do the forward pass. And you see the nice animation I did there. You calculate all the X's. They were grayed out before. I don't know if all of you appreciate it. It was grayed out and now it's black, okay? And so we calculated all those X's through those forward weights, okay? And we can also calculate all the way to the loss. We now know what the loss is, like with respect between the output, like the prediction and the label. Now we do the backward pass. So we didn't have those G's before, and now we just do this backward pass exactly by the way that we just discussed. So we multiply, so we go each layer, we multiply by the derivative of the activation, which in the ReLU case means for each neuron just ask, is it on or is it off? Should I kill it or should I leave it on? Then I multiply by the matrix, go again. Who do I kill? Multiply by the matrix, okay? If it's not ReLU, if it's sigmoid, then the derivative is this number that you need to each of them to multiply by. After you got all your G's, you need, remember, G is the gradient with respect to all the neurons. You want the gradient with respect to all the weights and biases. So the next thing you're going to do is use this trick that we saw before, this split that we did, so that you got your G, then you multiply it by the derivative of the activation and by the matching X's. And I didn't explicitly show it, okay, for the biases. You can check it yourself, or just think about the biases a way that's always multiplying the value of 1. So this and this is the same, just that X is just equals 1 for all the values. Okay. And after you calculate the gradients, the last thing you do is you update the weights, okay? So you use the gradient descent rule and you subtract the gradient multiplied by the learning rate with your weights. Now your weights are updated and you're going to do the same thing again. And you go all the way until you're tired or you don't have GPUs anymore or you got the result that you're happy with. Are we good at this point? Yeah.
2 questions. One, assuming a small enough learning rate, are we supposed to get a self-persistent result, or is it supposed to continue?
No, because you start from random initialization. And this is by no means a convex function. You're not going to get the global minimum point. What theorists show is that with very, very high probability, you're going to end up a different set of weights whenever you reinitialize. But most probably, you're going to be happy every time. It's going to be different set of weights, but you're still going to get, the loss is still going to be good. You said you had 2 questions?
That's it.
Okay. Are we good?
Why is it not a convex function? I mean, the
Why
loss
is
is
it?
still a convex function.
I cannot tell you why this is not a convex function, because it's like proving you don't have a sister. You need to show me why it is a convex function, and I see no reason for it to be.
So the loss is still a convex function of the outputs, right?
Sometimes, most of the times, yeah. But then you got all this.
Okay.
Okay, and if you check, so you see it's what we call highly non-convex. In fact, it kind of looks, it's like, it has a lot of dimensions usually. It kind of looks like an egg card. So you have lots of minima. Okay. This was all the way up to here. We were discussing what we refer to as vanilla neural network, like the most basic multi-layer perceptron. I'm saying all the terms so that if you bump into them, you know it's the same thing. NLP, Okay, this like bunch of matrix multiplications and activations. It's the basic thing. But one of the most important things is that neural networks can be more than these vanilla neural networks. So we're going to get much more generic now. So this is like, so the first part was about this very technical NLP calculation, but now we're going to take things just abstract, more abstract by a notch, and to see how we deal in general with backpropagation. And this is important. And I'm pretty sure you're all going to know this very, very well. And the reason I'm sure about it is that in homework number 2, you're going to implement a neural network from scratch, and you're going to use those principles. So it's going to turn out really well, because you see this now, and then you're going to implement it, and then you'll be people who really, really know how neural networks work, as opposed to many people who just kind of know. So this was in 2018. Jan LeCun is like one of the Turing laureates, considered one of the, I don't know, one of the fathers of deep learning, or whatever you want to call it. And I remember seeing this post in Facebook, either the chief AI, whatever, Facebook. And I remember seeing this post in Facebook where he said that deep learning is not a great name anymore. And the reason it's not that great is that we're not just doing these matrices that multiply things anymore. We do much more generic cool things. So we need a new name for it. So Viva, differentiable programming. This didn't work. Nobody says differential programming, and everybody is just saying deep learning, which is cool, which is okay. Doesn't always work out for you. But the idea that this post represents still holds. We need those generic blocks. We don't want to just multiply by matrix. We want to do many, many cool things, as long as we can take backpropagation through them, and then we can have networks with various mechanisms or parameterized functional blocks that do many things. So let's get more generic now. And the way we're going to do this is we're not going to talk about vectors anymore. We're going to talk about tensors. And when I say a tensor in this context, I mean it can be anything. It's a creature, it's something. Okay? In most cases, it's going to really be like a tensor, like like a multi-dimensional array of values. Okay? Think about an image, right? We apply neural networks to images, and an image is not a vector. Okay? It depends on how I represent it. It might have like height and width, and those of you know RGB, so we have channels and whatever. Okay? So I have this tensor, and I call this X superscript 0. This is the input. And I can't divide it to those neurons anymore. I have neurons as functions, but I can't have this sort of neuron value. It's not going to be very consistent, although people still use this term. And as you know, we're going to have, for every tensor, we're going to have this gradient, okay? That's G that we had before. So in PyTorch, you take the tensor and you do point grad, and you get, and then it has the gradient value. So it has the forward value and the backward value. And I'm going to apply some transformation to it. I don't know what it is. It can be anything. Not anything, but it can be many things, okay? And just like before, we had the matrix of weights, things don't have to be linear anymore. So now what we have is this sort of transformation T applied to it. It's the layer L+1 applied to the layer L. And I go through it and I get the next layer, which is X super 1. But here's the thing. Most, not all, most of the actions that I want to do have parameters. So for example, if you think about this, the matrix multiplication we had before, so the matrix itself is the parameters, right? So actually, x1 is the output of two things through this function, of the input x0, but also of the parameters w. Okay? So we are starting to think about layers as functions that get both parameters and input values, and then they output the next layer. Okay, so you see it's a function of two things, also the parameters. Now I want to look at the gradient. Okay, I want to be able to optimize this thing, and we already know how these things should work. So I need to find what is the gradient of XL. So by definition, it's the derivative of the loss with respect to x. But I can, but I do the same old trick, splitting it, you know, this thing, and I'm saying, okay, but I'm going to rename it, and I'm going to use the L, the XL plus 1, the XL plus 1 to the XL. And there is no summation here because it's not a neuron, okay? It's this entire tensor, and I assume at this point that I only have this single flow direction, okay, this architecture that you see, okay? And this thing is just the gradient of XL plus 1. So I'm doing the same process that we did before. I don't know if you noticed, only more abstract. So before it was multiplied by the derivative of the thing. Now it's all more abstract. So it's all just names, okay? So DL over DXL plus 1 is just XL plus 1 point gradient, okay? Just like this definition. Are we good? Okay? Did you lose me? Are we okay? Doing good? Anybody question? Yeah.
The transformation, you said transformation G, but then you said T1 is like weights before. And what is G before? G is this gradient? Or?
Yes. So G is short for grad. I'm sorry, so I didn't have room enough to put in grad. But
No, we didn't do anything more than we did before.
no, it's just more generic. So I'm not saying now this T is multiplied by anything. It can be anything. Okay. All right. So this basically means that I need some kind of a way to get this derivative. So I want to go from here to here. And we used to have this formulation. We did this together. Remember, you told me the derivative of the activation function, whatever. I can't say this thing anymore because I don't know what T is. Whatever T is going to be, I will also need to have its derivative. So the rule is, when one of you comes and defines a new layer, a new action that I want to use inside a neural network, I also need to define the back transformation. So every such function is going to have its forward method and its backward method. Okay? So the forward is just what we previously named just as T, but the backward is now going to get the gradient of x1 in this particular example. Okay? And the backward is usually I'm going to define it as the gradient of just as we defined before, but in some crazy cases I can use the backward not to be exactly the gradient. For example, if I really want to use something that is not differentiable at most of the places and I want to do some estimation or some weird tricks, but in 99% of the cases I'm going to define it as the gradient, and then I'm using the backward function, and its definition is that it gets you the gradient of x0 when it gets the gradient of x1. Okay, so it does to G, to the point gradient, exactly what the forward functions does to the x. Okay, in most cases, in most of the actions that you're going to do, like in PyTorch or whatever, this happens automatically. So PyTorch knows almost all the actions that you're going to do, and it knows how to pair them with the backward. So if you say, I don't know, A equals B plus C, it knows already, as long as A, B, and C are tensors, it already knows to construct this graph and and that there is a back process. But if you define something new and crazy, okay, that is not made out of these blocks that PyTorch already knows, then you will have to do it yourself and define this backward function.
Why will it depend on XL?
Because sometimes, so think about it as the gradient, you would want to define the backward function using this value. So for example, if you have if you have some transformation T that uses the input X to calculate something, it might be that the gradient also depends on it. So for example, think about the derivative of the activation function. Okay, the derivative of the activation function is a function of the inputs to it. Okay, so when you multiply by it for the gradient, you're going to need it. All right. But what are we missing here? Remember the same thing we were talking about before? We don't care about gradients with respect to those tensors. What do we really want? It's now grayed out.
Loss function?
The gradient with respect to the parameters. Okay? And the way we're going to do this is pretty the same as we done before, meaning that the backward function also needs to be defined such that it also returns the gradient with respect to the weights and not just with respect to the input. This is how it's constructed always. Okay? And this is why I'm saying it's healthier to think about this function as a function of both the parameters and the input tensor. Okay? Because if it's a function of this, and then I calculate the gradient should be with respect to all of these, to all of the inputs. Okay? Are we good by now? So this is like a more generic way of looking at it. So it's actually easier now because you don't have to go through like the derivative of the activation of the whatever. It's all very abstract. It's just, I have these building blocks, these functions, this transformation. They all have a forward method and a backward method. And yeah, the backward should be the gradient. This is what we just learned. But it doesn't matter when you practice with this, okay? It just has this backward. And when I do the forward propagation, I use the forward functions to get x1 out of x0, or we can go on and do this. So here is how you train a neural network in a more generic way. So at the beginning, all I have is the input. So I have the input x0, and you see everything that is grayed out. I don't have it yet. I don't have the x0 point g. I apply the first layer. So I go through the forward, okay, and I get x1. Then I go to the next forward, and I keep on going. Oh, and I didn't mention that each time I need to take both the input x and the parameters. They go in, I apply the forward, and I get to the last layer, my prediction. And now I'm going to get into the loss function. Note how the loss function doesn't have parameters. Okay, it doesn't make, you can do whatever you want, okay, but it doesn't make a whole lot of sense to have parameters in the loss function. Think about it later. But what is missing here? What do I need except of what I have if I want to calculate the loss?
Why?
Exactly. Why? The label. So usually it will look like, not always, you can do whatever you want. I don't know. You can have a neural network that you're trying to always calculate just 0. I don't know. But usually this is how it would look. So the loss function is a function of both x and y. And the loss function is also a function like all the others, and it has a forward and it has a backward. I'll calculate the loss. This was the forward process. Okay? Now comes the time for the backward process, the backpropagation. I calculate the loss and I go through the loss function's backward method. Typically, it's going to be something. So if this was MSE, it's going to be twice the difference between x and y, whatever. Okay. But it can be anything as long as you define it. I go through the backward, and look at this. I have my first gradient with respect to to the prediction, okay? And I keep going. Now this backward is going to calculate two things for me. It's going to give me both the gradient with respect to W and the gradient with respect to the layer before. And then I keep going, and without even noticing, I don't need to do anything else. I already have all I need, the gradient with respect to all the parameters in the network. So this happens within this flow. Okay, so in that specific old case, the vanilla case, I explained to you that we do this with respect to the neurons, and then we take this peak, and then we can do with respect to the weights, because it was very specific function. But when it's all generic, it's just the backward functions should provide you the gradients also with respect to the weights. So you got the gradients. All you have to do now is the gradient step. Okay, like the gradient descent step, where you take all the weights and you subtract the gradient multiplied by the learning rate. You have a question there? Sorry? No? Yes. You mean like Adam and things like? You mean like Adam and all of this? Sure. Yeah. There are. I mean, there is a limit to how general I can go. It also doesn't have to be a neural network, right? There are other but this is for basic SGD. And you're right, there are other optimization methods that are also gradient based, and you learn about them, and then it's not this, but you see like divided by things and multiplied by things or some other stuff. But yeah, sure. Yeah.
Do you include a bias in the weights?
Yeah, I don't talk about weights and biases anymore when I go this generic. I just have a bunch of parameters, and this can be very diverse. This can be, so you think about weights and biases because you think about multiplying by a matrix and adding a bias, but this can be, I don't know, maybe this layer takes the input and then it takes the input to the power of the parameter. Can be whatever you want it to be, okay? So it's just a bunch of parameters, and this can be, so if this can include weights, biases, whatever you want to name, it's like a bunch of numbers that do things to the input.
So now weights are not the numbers, but parameters are.
What do you mean they're not numbers?
Like, okay, can you like elaborate on like what is the parameters and what is weights? Like
It's just names. So sometimes we call the parameters weights, but it's more, usually weight is something that multiplies something. So maybe it's like, it's not a great notation, and parameters is like a better general term for just things that do things to the input. So they can multiply it, you can add to it, they can take, I don't know, power to it, whatever you have in this, you have a function, and the function has parameters.
So they're both learnable. So like there's no so big distinction between weights and parameters.
No, weights are parameters. Okay. Okay. So, so this is the structure that we have. Okay. Everything is just about the sequence of blocks, and these blocks always have a forward method and a backward method. When you do the feed forward, you just apply all the forwards in sequence. Then when you want to calculate the gradients, you do all the backwards. Question there?
W here is composed from all the weights of all the layers.
You mean this W?
This W.
Yes. Yeah, you're right. Yeah. Maybe I should have had like indices. At some point I become lazy. Okay. Let's see now, let's connect the first part to the second part. So for example, the standard MLP layer that we've seen before can be constructed this way. So we have this linear, this is matrix multiplication, and then we have a ReLU. This has no parameters. Okay, there are layers with no parameters. It's fine. And this is how it's constructed. Okay, the linear layers. These parameters here are actually this weight matrix, okay, multiply, and I get this, and this is what we had before. So the backward here would have to be the thing we calculated before, okay? If you think about these two backward, if you just take this, then the backward is just multiplying by this vector. And if you think about these two, this backward is multiplying by the derivative of the activation function, the relative, which is multiplying by either 0 or 1, depending on whether or not this was positive or negative. I mean, this was positive or negative.
So you're separating the original one into two steps?
Yes, just as an example that we're looking at here. Okay? And this becomes cool. Okay? Here are some very cool things. So by the way, you don't have to have this structure of layer after layer, this sequence. You can do this with any directed acyclic graph. Okay, that directed acyclic graph. What you see in this example, okay, we call this a skip connection. So what's happening here? I multiply by a matrix, I apply ReLU, then I add the result to the original input I had before. This is called a skip connection. Can I optimize this? The answer is yes, I surely can. And I just remind you what we already know is you can think of these nodes that we were thinking before as about neurons as tensors, as full tensors now. And the main thing I want to remind is this summation thing. So think of this X now as the input here, and there are two gradient paths that point to it. Okay? So you see we're getting two of these red arrows now. And the way to mitigate this is simply by add them. So you get your gradient contribution in this sequence here. You also get it from the skip connection, and the true gradient, the true derivative of the loss with respect to this tensor is just adding them together. Okay? Always think about the intuition. Derivative simply means if I change X by a little, what happens to the loss? And the thing is that it influences through two different routes. If I change X by a little, it goes through this sequence and changes something here. And it also contributes to the change through the skip connection, and then the change is the sum of both of these together. Okay, so this is called a skip connection.
What is the loss in this example?
You don't see the loss. You need to think about it as this keeps on going, and then there is some loss. Okay.
The two entries.
The two entries to what?
Of the two entries.
Oh, so you see when I look at this layer, the function of this layer is going to be this thing applied to X plus X. So think of this function, how you take its derivative, you see X twice, you see it. So if you, let's say all of this is called F, so we can say that the outcome here is Y. So we can say Y equals X plus F of X. Then the derivative should be the partial derivative of Y with respect to X plus the partial derivative of Y with respect to F of X multiplied by the inner derivative, right? So this is exactly what we're seeing here. This, what I'm really emphasizing here is this plus, okay? You get both arrows and then you just sum it all up. As a matter of fact, the way to go is that you never erase gradients unless you specifically do so. So you see that when you optimize, you can run this even a few times in some cases. Gradients are always accumulated unless you zeroize them. So in PyTorch, for example, you have to specifically do zero grad. Okay? So if you didn't, everything is accumulated. By the way, too, and this is super elegant, I think. Okay. This this is where everything becomes really practical. This is like functional programming for those of you who encounter this. This is really cool. I can rep whatever I do, whatever sequence or graph that I have, I can wrap it up and just call it a layer. It has a forward method. The forward method is go sequentially through all the forwards, or going forward through the graph, maybe is a better term because it doesn't necessarily sequence of layers. And the backward is just going through all the backwards. And now I can think about it as some sort of a black box. I don't care anymore. And I have this thing, I name it. It has a forward method, it has a backward method. And this is it. This can be an entire network. My entire network is also like a layer. A single layer is like a layer. Most of the actions that you use, you don't know, but behind the scenes, they are constructed of parts of layers. For example, the MLP layer that we talked about before has two parts, right? It has multiply by a matrix, then apply the activation, and add bias also before. We can say even three, right? You can wrap up whatever you want to have your layer, and it's constructed in this hierarchical thing that when you look inside a layer, usually you'll see it constructed by more layers until you get to the sort of the bottom. Okay, and then you make up whatever you want. I have a network that does something really cool. I want to use it as part of another network, another thing that I'm doing. I'm just going to put it there, and I'm going to go and I can optimize everything else. I go through the forwards when I do the forward pass. I go to the backward when I do the backward pass. Are you getting how elegant this thing is? Extremely elegant. Okay, it's very nice. All right. Here are some life lessons. So, can we eventually use any function in a neural network? What do you think? Can I do whatever I want? So that's one point, right? So it needs to be differentiable, or at least such that I can do reasonable estimation for something that is sort of its gradient. But there are other implications, and I was affected by this. There was many years ago by Andrei Karpathy, like an important person in our field today. And back then, I think he was actually a PhD student. And he had this blog post saying, named, "Yes, you should understand backprop." And this affected me. And to this day, I remember one example that was there. And I want to give this example and then another example of my own. And these examples, they show you why it's not automatic, why you need some considerations and why you need to be thinking about backpropagation and about gradients whenever you practice deep learning. So here's one thing. So he was telling in this blog post that he saw this network and it was, I think it was outputting images and it needed to be clamped. So the output value has to be between 0 and 1. And they wanted to train it as such. So they said, okay, fine, we have the network, it does whatever it does. And now we're going to add this one less layer saying, let's clamp it. If it's bigger than 1, make it 1. If it's smaller than 0, make it 0. What do you think about this? Is it okay?
No.
Not great. Okay.
It's not defined.
It's not defined?
The range between 0 to 1 is not defined.
No, between 0 to 1, just leave it as is. Identity. So this is how the function looks like.
You have a layer that the gradient is 0, right?
What?
You have a layer that the gradient is 0 for almost every value.
Yes, exactly. So think about this. I have my network. I'm starting the training process. It starts randomized. So maybe when I start the training process, the values are all like 20 something. Nothing is going to change. The gradient will be 0 all the time. So in the gradient descent process, the weights are not going to change, the parameters are not going to change, and I'm going to be stuck forever. If I'm lucky and it's here, okay, but everything that got out of the range of 0 and 1 is just not going to affect the optimization. Nothing is going to move. So this is one example. So you shouldn't do this.
You could initialize everything between 0 and 1.
No, because this is the output. I don't know what the output is going to be. And if I did, I didn't need all this network thing, right? And anybody has a suggestion? What would you do if you needed to do this? Nice, exactly. So sigmoid is was I think I mean sigmoid is like almost 100 years old or something, I know, but I think it was invented as sort of the differentiable step function. Okay, kind of okay. Here's a thing that happened to me once. I desperately needed some loss that encourages sparsity. And when you think about it, you can encourage sparsity by using, like you have norms, so you have L2, L1. If you're taking L something that is smaller than 1, like L half, then you encourage sparsity. L half means taking square root. So I was thinking, let's use a square root as a loss. And I want to show you the problem here. This is how square root of the absolute value, whatever, okay? This is what it looks like, okay? And now we don't have this problem anymore, but does anyone recognize any type of problem here?
As you approach zero, it becomes near infinity. So if you
Yeah.
have one of these points, it's going to
Exactly. It goes crazy. So let's say I start optimization and I'm first here. This is fine. I calculate the gradient. This is the direction. I go here. Okay. Now I'm going to get a very big gradient and I'm going to jump over there. And especially when I'm close to where I want to get, then the gradient becomes infinity. Okay. If you think about it, MSE, so L2 norm, is quite the opposite. As you approach, you get smaller and smaller gradients. L1 is naive, not naive, it's agnostic. Okay. It's like, it doesn't care. The gradient will always be.
Well, you do get sparsity out of it.
What? Sorry?
You do get sparsity out of it, right?
I mean, you get none and everything crashes. I don't know. This is sort of sparse.
Why is the jumping not good and ReLU is if you are in the
I didn't say ReLU. I say sigmoid. But
yeah.
But ReLU is not the same. It's not quite the same thing because in ReLU you have. So think about it. Every time you're going to get different input to the ReLUs, and then some of them are going to be negative. They're going to be killed. They don't have a gradient. Remember, we said we saw it live. You multiply by the gradient of the activation function, and when the ReLU is off, the gradient is 0. So that's a true observation. But the thing is, there's also the positives one, the positive ones. So you only get gradient through the positive ones, and you kill all the rest. But in this situation, you limit and you put it on the loss at the end of things. So you're not going to. So if everything is out there, so you write, for example, that if you, for some reason, when you start your network, you use ReLUs, say after the first layer, and everything is extremely negative, then you're also sort of stuck. If for every input that you have, but this is kind of unlikely. But you do get some. You can read about. There is a thing called dead ReLUs. So it can happen at some cases. How much time do we have? Oh, not much. So the message here was that you can be creative. You can make up your own layers, put very creative stuff, but you should also always be thinking about the backpropagation. Okay. What's going to happen on the derivative, even if everything is legal and automatically differentiable, like when I use square root, I didn't need to define the backward for square root. It already exists, but still, this situation, things will not work out for you. So you need to be aware of this. So until we get kicked out, I'm going to use very quick few minutes to show you example. You can go, so you have the link there. And this is like a neural network example. And when I have no hidden layers, oh, you're not seeing this. Oh, I feel like we're not going to have time for it anyway. Okay, I think we'll wrap it up like this. Okay, so I'm just going to let you know that in this week's tutorial, you're going to have Raphael, and he's going to teach you about PyTorch. Then, unfortunately, you're going to see me again next week, and we will be talking about convolutional neural nets